So for this part of Module 2, we're going to look at some structural issues around our cassettes. So I have two illustrations of cassettes here. We have a rectilinear common type of module system, very typical. And then I've just shown as an illustration just to keep us thinking about this, these non-standard, almost parametrically variable facade elements. And the idea here is we want to look at really specifically one specific issue about structure on it, but in the context of all the other issues that would be applied to this. So there's a lot of activity or actions that are working on our facade. We have two section views here and an elevation view. And the red one is the one we're going to actually do some calculations on, but I want to make sure that we're clear that we're sitting in a constellation of issues about structure on the facade. So we have gravity loads on the facade, just the sheer weight of it having to be supported just like any curtain wall would be supported, in the clips and the loads that would be applied with that. We also have this idea, when we're looking at the facade and elevation, that the building, these cannot act as shear walls, so they are kind of floating within their support systems to a certain extent. So they're subject to racking and seismic forces being placed upon them. So we need to make a consideration for what happens when these loads are applied and when the deflections that happen within the normal flexibility of high-rise construction. But the primary one we're interested in is this idea of what happens to our facade when it's deflected under wind load. And I picked this specifically because the idea is that under certain conditions, this deflection would become an occupant's concern. I mean, obviously, if this was so flimsy as to be a curtain of fabric, its deflection would be quite unnerving in a high rise. And so we want to think about how that, how much it's going to deflect and what the implications of that might be. So we have a uniformly distributed wind load. We'll get an idea of how we would calculate that applied to our facade. And then we think about how those wind loads are supported back to structure. So we can look at that idea of our assembly as a more resolve-free body diagram to being a simply supported beam, with the two supports being the floors, and the uniformly distributed load is a constant uniform wind pressure along the surface of it. Whereas a lot of things we're not doing in this calculation, we're really not implying that we're doing any kind of engineering here. We're really just kind of looking at what the effects are of a design that we have on what the performance of our facade might be for one specific condition. We're not dealing with buckling. We're not thinking about glass deflection and structural components of that. We don't look at the glass as adding to the structure of our assembly. So there's just an idea of primarily here is to think about how deep does that panel need to be if it's made out of a specific material in order for it to have reasonable deflections under some kind of design wind load. So the idea is we're going to work through and create a spreadsheet, a Google Docs spreadsheet that you could reuse for all kinds of applications. And I wanted to recognize that Jonathan Ashorn from Cornell had a website, and that's where I got this idea of making spreadsheets. And he had a calculator that he has created for all kinds of structural loads. And this is hyperlinked if you have if you download the slideshow, and so you could take a look at his site. It's really very well done. So we're going to look at building a lot of these calculations ourselves, and we'll talk about them part by part going forward now. So calculating deflection. We have these charts I'm sure you're familiar with your structures courses, and I've identified the condition that's close to what we want to do here or is identical. The idea is we have a simply supported beam with two supports and a uniformly distributed load. We have formulas now for the maximum moment, the maximum shear, and for the deflection. And so what I want to do is capture that formula onto our spreadsheet. I also want a way to calculate what our wind pressure is according to wind speed. And I Googled and found quite a simple calculation here. Our wind pressure, P, is equal to this, the velocity of the wind in miles per hour squared times a coefficient. And that gives us in pounds per square feet, which is very useful for us because we're used to the empirical values are I'm at a loss. Imperial values for are not metric for many of our calculations. And you'll notice here at 70 miles an hour, we get 12.5 pounds per square feet. And that kind of correlates very closely with a little bit of research I did. I found that glazing systems, and this is, I probably captured this from another document, just as a touchstone to reality. Glazing system was designed for 20 to minus 20 pounds per square inch wind loads, typical condition. They talk about corner loads, which indicates that there are other issues in building design that we might want to consider. And also what's unique about this is that it's plus 20 to minus 20, which indicates that not only do we think about the forces from the wind load, but the negative pressure that's created in high-speed wind systems like this, that'll actually put negative pressure. So there can be just as much pressure pushing out as there can be on one side of the building as there is on another face that's experiencing the wind. So, but these numbers correlate very closely with these, so I'm comfortable with using this calculation. So we're going to build this chart up. It's nothing more than putting all the different wind speeds down, using that formula to create our pounds per square feet. I've added some labels to it, like the idea of this is where the code is typically sitting, and then this idea of category 4 down here, these high wind loads. I bring that up because every year it seems like there were 2 hurricanes almost approaching in the Gulf Coast this year, and the wind speeds were 145. It hit landfall as a Category 4 storm, so that would mean that it had wind speeds in the 130 to 150 mile an hour range, and so these are significant impacts that our code is not designing for currently. And this may mean that we either, as designers, want to think about designing better than code, or we need to be aware of code changes in the very short future and how that affects design. So just like a floor system, we need to identify that tributary load area to figure out how much our unit is being expressed upon it. And so we have we'll take one of the side edges of the cassette and look at the tributary load, which is half of the load from this side, half of the load from that side. In this case, it's 15 feet by 5 feet, and it gives us 75 square feet. We can take the wind pressure and come with a total load on it. In this case, I use 75 pounds, or excuse me, 37 pounds per square foot as a design load, and came up with that. And that's kind of related to where our code has required that. It's important to note in this chart, and I'll show you on our spreadsheet, it's a parabolic shape. It's an exponential rise in the amount of energy because it's based on the square of the velocity of the wind. So we have, in this case, it's a little misleading because the last step I make is to 155, which is the end of our recordings of categories of wind speeds. So this looks a little sharper, but this would have been actually much higher here. So you'll notice the differences here are very small, and then they become really quite significant at these higher wind speeds. We also need to know section properties. This tells us how deep we're going to make our section in order to establish the performance we want. So I've just grabbed a chart that has, this is cold rolled steel probably section, but it's fine for this. It was easily available. So we have the idea is C15 by 50 is a 15-inch deep sea channel by 50 pounds per feet. And that gives us a section property, a second moment of inertia that we can use to calculate deflection. We also need to know what kind of material we have because of the modulus of elasticity. Typically in these cassettes, we're making them out of aluminum because we're extruding these profiles, these complex profiles. So we have the idea of probably using this value. But we could be using steel, especially if we had to do some kind of reinforcement. So I wanted to capture the idea of what the value for steel was also. So here's a first comprehensive look at the spreadsheet I want to build. Like I said, it's a Google Doc spreadsheet. We're going to input some data, calculate some data. We're going to bring some reference sources in so that we can use those to create these elements over here. And we're going to build a wind speed chart like I showed you before. And I guess here's a little close-up of that. And that will move me out to the actual spreadsheet, and we can kind of review that. Because this is all video, you can go back and look at specific issues as I discuss them if I go too fast. So we create a chart with labels our wind speeds. This is that calculation I showed you. So we have the wind speed value squared, that's that's the power function right here, times that coefficient to come up with pounds per square feet. And then we just duplicate that calculation all the way down. And then we connect that to a chart that we create. And I'll leave it to you on how to create a chart. I think these are all great learning exercises for you. But if we go to edit chart, we'll get up in the chart creator. We can make all kinds of charts that have values and labels to these axes, and I've left mine fairly simple. We actually don't need this chart in our calculations, but I wanted you to create it just to see how you could take see this actually exponential rise in pressure with wind speed. Because over here in the meat and potatoes of our calculation, our ultimate goal is to look at the deflection of our beam. In this case, it's 0.8 of an inch, a little over 3/4 of an inch, at a wind speed of 150 miles an hour, which is an extreme event, which is an extreme deflection. So let's start down here. We take our wind speed. We can put any value we want in here. If I put 10 in here just to show you. Okay, now all of our values go down, and now we're less than 1/1000th of an inch in deflection at 10 mile an hour wind speeds. I'll just go back to the 150 because that just makes it a little more dynamic looking. So I'm taking wind speed times the square of the wind speed, which is part of that calculation, times its coefficient. And I'll just show you these. This is an input value. This is this value squared, the 150 squared, and then this one is that 150 squared value, this value here, times that coefficient to come up with pounds per square feet. So we have now an idea of a wind load that we can use to create our total load on our window structure. So we take our panel width, in this case I've assumed 69 inches, our beam length, the height of it from floor to floor, at 180. I'm not exactly sure why these values are in the initial start of this. This could be 60 inches, and this could be, if we had 12-foot floors, this could be 144, and that would affect our deflections here. And you'll notice this, if just for sake of looking at this calculation, if I greatly increase the floor height, you'll notice our deflection goes way up. So I'll go and turn this back to 44 inches, which is 12 feet. These two values are in inches because that's how the calculation works using units in inches. So we cube the beam length, which is part of the formula. Then we're going to have to multiply it by the applied load, tributary load, which we calculate. And then in order to get this deflection, we just put all of these numbers into a calculation to come up with this deflection. We have a place to put our modulus of elasticity in. We have a place to take our section property from our chart. So if you look, it's 47.6. I have pulled that from the chart. I'm having a hard time finding it. I don't see 47.6. I see 47.9. So that might be a typo. So that would have been, let's see here, that would have been a 9-inch deep channel. Made out of aluminum. In this case, because I'm using 9,900 kips for the section of the modulus of elasticity. So let's once again. So we have that beam cubed. Our tributary load is our 160 times 144, and I'm dividing it by 144 because I'm now trying to create it instead of pounds per square inch or units per square inch to square feet. So it's just converting us back to feet by dividing by 144. And then I'm multiplying it by B23, which is our pounds per square feet, which gives us our total load. So you'll notice if I change this value to 120, and hit return, this load will go down. And I'll just undo that. So we can, at any point, we change our wind speed, we change our spacing, we get new deflection values that come up over here. So that's our modulus of elasticity, which is just input as a direct number. Our second moment of inertia, once again to review, is from a section property of whatever C channel we want to use. And then we come up with a deflection, which is an L over a certain number that gives us whether our deflection is within limits. This one is not really critical for us, but this is a touch base. In architecture floor loads, L over 360 is considered an allowable load of deflection of a floor to feel comfortable, sometimes L over 480. So in this case, this would be, if it was a floor, this would be an acceptable level of stiffness to a floor system. So you can use that as a touchstone to whether the stiffness of the wall system is falling within a normal understood range in architecture. So let's now specifically look at the final calculation. And you can see here it is 5 times B7, which is the load, times the length cubed, which we've already done here, which is B6. All right, all divided by 384 times our B8 value, which is our modulus of elasticity, times our B9 value, which is our section property, our moment of inertia, second moment of inertia for our channel that we selected. So this is automatically giving us, not automatically, this is giving us our deflection on our beam. So that is really the whole chart. I would like you to recreate it and understand it and be able to think in the future that you could create similar charts like this to do some kind of analysis of a critical component that you might be designing. Let me see if there are any more slides before I complete this. And that completes that section.